7 people register for this. Let's see how many show up. Seven people. Yeah. Okay, one more minute and then we can start the webinar.
Good.
Okay. Okay. Good morning, everyone. Welcome to today's webinar. My name is Kabir, and I'm with Bandlever Research Group. I will be your host for today's session. We got an amazing speaker joining us today, and he will be talking about adapting of unpredictable spring, flexible planting strategies. Before we get started, I'd like to take a moment to thank all the counties that fund and support us. Because of them, we are able to offer webinars like these that bring valuable information out to our producers. Just a couple of quick housekeeping items. If you have any questions during the presentation, please hold them until the very end. We will have 15 minutes for Q&A. If something urgent comes up or you need my help during the webinar, feel free to drop it in the chat. I will be keeping an eye on it throughout the session. All right, it's my pleasure to introduce our speaker, David Sachin. David is a director of Prairie Adaptation Research Collaborative and a professor at the University of Regina, focusing on prairie hydroclimate variety and climate change adaptation with over 500 invited talks and deep prairie roots dating back to early Alberta settlers. Over to you, David.
Thank you, Kabir. And thanks for inviting me to speak to your group about the climate of central Alberta and how it's presenting opportunities and some risks for agriculture. This picture, this place is in the county of Flagstaff. It's about 4 townships east of Forestburg, near Bells Hill Lake, if you know where that is. This picture was taken late 1950s, probably early 1960s. You can kind of tell from the vintage of the pickup truck down there. That's the mail truck back when they delivered mail to every farm. And this is the way I remember the farm when my grandparents were still there. Very much a mixed farm with great place to spend the summers as a kid because there was cattle and hogs and a couple dairy cattle and chickens and a huge garden that my grandma had, and all cereal crops, of course. Back then, there was no canola, at least not on their farm. Yeah, it was. This is how I remember it, but lots has changed since then, including the climate. You probably saw these headlines early this year, where all these news outlets reported that 2025 was one of the hottest years ever recorded, and there was CBC was also suggesting that 2026 also will be one of the hottest years on record. It's interesting stuff, but I'm not sure what we're supposed to do with this information because the Earth doesn't have a climate. There's not a single climate. This is a statistic from averaging data from thousands of weather stations. This is the data as compiled by NOAA in the US. And this graph is the average temperature of every month, right back to January 1880, right up to the end of last year. And it's shown as anomalies, so the difference from the 20th century average. If it was a warm month, it's shown in red. And if it's a cool month or a cold month, it's shown in blue. And what's pretty obvious is that ever since the mid 1970s, every single month has been warmer than average, with one little exception in, I think, 1985. You can see that tiny blue bar. So this is pretty convincing evidence that there's more heat being stored in the bottom of the atmosphere. But like I said, there's some limitations to this diagram because a global average is simply a statistic. It doesn't actually exist. When you grab your phone and look at your weather app, you can't find the weather, can't find a temperature of the whole world. So you have to keep that in mind. And also, when people look at this, they focus on that big block of red off to the right, and what they see are these peaks. They don't necessarily notice the valleys, so that there are some years that are warmer, or sorry, months that are warmer than average, but not by much. So there is a lot of variability from year to year, which is perfectly natural. But for people see this, they see the upward trend, they read the headlines and they think, wow, it's getting hotter. And the biggest misunderstanding is that people think it's getting hotter every year and everywhere. Not necessarily. As I indicated, there are years that are not much warmer than average, but also it's not getting hot everywhere. It's getting warmer at a faster rate in some places than others. So, and also we don't make our decisions based on the temperature of the whole world. We make our decisions based on the temperature where we live. So let's look at central Alberta. Let's look at the weather of central Alberta. And to do that, I want the longest possible weather record because by definition, climate change is a shift in weather that persists for decades or longer. And this is something that a lot of people don't seem to be aware of, because if we get a warm year, they think it's global warming. If we get a cold year, they think it's not global warming. No, that's not climate. It's weather. So you have to have decades of weather data before you can derive any kind of statistics, because after all, climate is the statistics of weather. Climate is the average, it's the range. And so you need a relatively long weather record before you can derive any kinds of statistics that suggest that the climate is changing. And in central Alberta, in fact, throughout the prairies, the longest and best weather records tend to be at the Ag Canada research stations, which were established 100 or more years ago, and unfortunately are being cut back as we speak, according to the federal budget. But that's a different issue. So the Ag Canada research stations tend to have great weather records. So let's choose Lacombe. The Ag Canada research station in Lacombe, where there's a weather record going back actually much for longer than this, but I've just shown you the last 105 years. And this is the daily maximum temperature. So this is the highest the temperature got on a single day every year. It's showing that the hottest days we had in central Alberta were in the 1920s and 30s. And in fact, if we choose a threshold, let's choose 35 degrees, and let's just say 35 degrees or higher is a hot day. Well, there's been, according to this, one hot day since the 1960s. And prior to the 1960s, there were a bunch of years in which temperatures exceeded 35 degrees, even approached 38 degrees. Now, keep in mind, we talk about how the temperature gets to 40 degrees. Well, yeah, maybe in the sun and maybe in southern Alberta, Medicine Hat, but where temperature is measured, which is in the shade, and in central Alberta, the warmest it's been is officially 38 degrees, and that was back in the 1920s and 30s. So the fact is, if you use this criteria, if you say, okay, single hottest day, it's not getting hotter in central Alberta. And this is consistent throughout central and southern Alberta and Saskatchewan. And there's been some really interesting research done by scientists, including at Ag Canada, that suggests that this might be the result of a change in land use. So as you know, back in the 20s and 30s and right up until about the 1980s, there was quite a bit of summer fallow. Land was left fallow in the crop rotation every second or third year. And fallow land was free of plants, and it was black soil exposed to the sun. And so the soil temperature was elevated by the practice of summer fallow, and the hot or warm soil led to warm air. And then starting in the 80s and ever since then, there's been much less tillage and more permanent cover. And so we might have actually cooled the climate compared to what it was early in the 20th century. Interesting idea. But as a result, the Canadian prairies are a bit of a strange case. They are kind of bucking the trend where we don't get the kind of very high temperatures we had back in the day. So this is a single hot day per year. This is number of days each year when the temperature got above 30 at Lacombe. And once again, back in the 20s and 30s and right up to 1960, 1961 was a wicked drought. It was a really dry year. And the hottest years are always the driest ones because, of course, water has a cooling effect. And in the absence of soil moisture, then there's less of a latent heat transfer, and there's more sensible heat that the heat that is actually measured by a thermometer. And once again, back in the 20s, 30s, and 40s, it wasn't uncommon to have 10, 12, as many as 17 days above 30, whereas since the 1960s, there's been relatively few years with long hot streaks. Another indication that our climate doesn't seem to be getting hotter. However, winter is a completely different scenario. So we looked at maximum temperature. This is minimum temperature, daily minimum temperature. I'm not going to show you the absolute minimum values, but rather the average for winter. Winter is December and the following January and February. So the average of those 3 months of the minimum or nighttime temperature, actually the temperature typically that occurs just before sunrise. Note that the values go from -11 at the top to -25 at the bottom. So the length of the bar indicates the minimum temperature, and the longer the bar, the colder the winter. And so we just get very almost the reverse scenario to high temperatures. We get many fewer low temperatures. And I've put -19 on here. I just chose arbitrarily. Okay, let's say if the average minimum temperature is below -19, it's a cold winter. Well, if you use that criteria, in the 21st century, there hasn't been a cold winter. There was one, I think it's 2015 or thereabouts, where the average temperature got down to -19. But prior to that, there were many, many winters in which the minimum temperature dropped on average below -19. Okay, so we conclude that winter is getting less cold. Here's another, and this is, of course, weather data. This is weather station data. So if you want to dispute this data, then you don't believe the weather forecast. It's the same information. This is weather recorded data. You can argue with this because this is a simulation. This is the same value, minimum winter temperature, but this is in the future. So we generated this using climate models. In fact, we used 11 climate models and took the average. And in the future is when the whole world has warmed by 2 degrees, which is probably going to happen by the middle of this century. If the world continues to warm at the current rate. And so by the middle of this century, southwestern Alberta, western Alberta will be about 2.2 degrees warmer in winter. But as you go north and east, you go up the scale until when you get to eastern Manitoba, it's almost 7 degrees warmer in winter, which is hard to believe. There's this huge discrepancy between across the prairies because, of course, southwestern Alberta is already and always much warmer than the rest of the prairies in winter because it gets Chinooks. So if you look south east of Edmonton, you're into that sort of beige color. So 3-4 degrees warmer in winter within the next couple of decades. Here's another indication that our winters are getting less cold. Back to Lacombe. The longest cold spell, the number of consecutive days when the temperature remained below -30. And again, back in the day, there were, 6, 8, 10, 14 or more consecutive days of -30. And that just hasn't happened in the 21st century. Our coldest winter, I think it's 2021, where there was 6 consecutive days below -30. So a big change in our climate on the prairies is we still get cold. We still get wicked cold in winter, but we don't get these long cold spells. And if you look at this chart and identify the coldest winter when there were 17 consecutive days below -30 at Lacombe, that was 1969. And I remember it well because I was there. Well, not in Lacombe, but I was growing up in Edmonton. And actually in Edmonton, there were 21 consecutive days below -30, since it's just a little bit north of Lacombe. And between the 7th of January and the 1st of February that year, those 26 days, the warmest it got, the very highest temperature was -21. And I remember that because I've had to take the bus or walk to school. And the Edmonton Journal, Yardley Jones, the cartoonist, came up with this certificate, and every school kid in Edmonton got this certificate. So it's just kind of hard to imagine a winter this cold. And so we conclude that our climate, the central Canadian plains, is not getting hotter. It's getting much less cold. And of course, there's lots of implications of that in terms of the snow cover, because as the winter warms, you can expect some of the precipitation to fall as rain, not snow. But also, if winter is less cold, it's going to be shorter. So the last frost in the spring should occur earlier, and the first frost in the fall should occur later as well. So you would expect in a warmer climate there to be a longer frost-free season. And in fact, that's the case whenever we calculate the length of the frost-free season for any location on the prairies, like Lacombe, we find an upward trend. Now, there's lots of variability from year to year. It's all over the place. You can still get short growing seasons, but on average, the growing season is getting longer and there's more heat units, which of course is great news for agriculture. We live in a cold climate. We live in a part of the world where one of the major constraints on growing things has been the length of the growing season, the heat units, and that constraint is being alleviated. But of course, and here's an indication of that. This is a remarkable data set we got from the Swift Current at Canada Research Station, where they've been measuring soil temperatures right back to 1963. Excuse me. And this is monthly soil temperature And the month is indicated by the color of the curve. And the thing to note is there's a group of months, the cold season, when soil temperatures are 0 or below. And those months, there's an upward trend. The other months where soil temperature is above 0 and as high as low 20s, there is no upward trend. There's a lot of variability from year to year. So in the cold season, soil temperatures are rising, which once again is generally good news for agriculture because you can expect the soil to thaw sooner in the spring. But the other part of the story is, okay, so global warming is making the frost-free season longer and kind of alleviating the growing season constraint in central and northern Alberta. But of course, you can have all the heat in the world, you need moisture. So here's the precipitation record from Lacombe. Extremely variable. All the way from, well, there was 1 year, 79. There's a few years in which the annual precipitation is less than 300 millimeters, and it's as high as 625. Huge range. But hardly any trend. I mean, I could fit a linear trend to this, but the linear trend would be insignificant compared to the huge range. So the dominant signal in precipitation is the variability, the natural variability, which really swamps any kind of indication of the effect of global warming. So people say, well, they can't see climate change. If they're talking about precipitation, I get it, because what we see is the seasonal and annual variability in the hydroclimate of our part of the world. So we have to. This is fantastic precipitation record, although precipitation is notoriously hard to measure, especially in winter and blowing snow. But this is a fantastic record. But we need other sources of information on precipitation before we can make any kind of statement about how it's being affected by global warming. So let's go back to the models. And this is work just completed by Zara Narisimale, who's one of my research associates, Dr. Narisimale. And she took precipitation data for the prairies from climate models. And the way to interpret these graphs, let's start with the top one. We have the percent change in precipitation on the prairies relative to a historical baseline. And the historical baseline is those 30 years, 85 to 2014. And then we're comparing the recent past to the near future, the middle future, and the far future, where the near future is the next 30 years, the middle future is the middle of the 21st century, and the far future is the last 30 years. And then this is percent change month by month. And if you look at any one of these plots, you'll see a shift in precipitation away from the summer and towards the winter and late fall. So a shift in precipitation from the warm season to the cool seasons. The total amount of precipitation doesn't change very much. In fact, it could even be increased a little bit. And it's funny how when people think of global warming, they think of heat and they think it's going to be dry. Yeah, but most of the heating is of the oceans. 3/4 of the world is ocean. And water has a tremendous heat capacity. And so most of the warming is of the oceans. If you warm water, it evaporates, and that water vapor precipitates on land. So we can actually probably expect, on average, in an average year, if there is such a thing, more precipitation. But that increase is in the cool season. Now, the difference between these three plots is the SSP, which is called the Shared Socioeconomic Pathway, which is what the whole world, that's why it's called shared, what all the countries of the world decide to do socially and economically, because that determines how much more greenhouse gases they produce. So the low emission scenario is SSP 245, 370 is intermediate, and the high emission scenario is 585, where we have the largest amount of human induced warming. And so you can see as you increase the emission scenario, the concentration of greenhouse gases, the model produces a larger disparity between summer and the cool season. And not only is that shift in precipitation, not only is that shift accentuated or amplified by warming, but also as you move into the future, to the far future, there's a larger shift in the precipitation. So this is quite, like it is. It's a projection. We don't even say prediction. We say projection is simulation. It's from models, although we use a lot of models. But it suggests that ag producers may want to take advantage of the extra precipitation in the cool season to withstand a precipitation deficit in summer. Now, this is for an average of 30 years. In any given year, there can be excessive precipitation or a severe drought. But we're looking at the trends, the tendency, because after all, climate is the tendency in the weather. Okay, so this is models. You don't have to believe the models, but you probably should believe weather stations, and you might also want to believe what the trees tell us, because trees are a plant and they need moisture, especially in our part of the world. And so annual tree growth is a function of how much moisture was available in the soil. And in our lab, for decades, we've been collecting old wood at every one of those green pins, more than 225 sites across the prairies, up into the territories and down into the northern states. But you can see there's a heavy concentration of sites on the eastern slopes of the Rockies, because that's where most of us get our water. If you live in a city or if you irrigate, then that's the source of your water. But also, this is where we find the oldest trees. That piece of Douglas fir has hundreds of growth rings, and the size of the growth ring is a function of soil moisture. For central Alberta, we have reconstructed soil moisture in the watershed of the North Saskatchewan River. So on your right, that's the Kootenay Plains, west of Nordegg. Amazing place. It's now an ecological reserve, so we got a permit from the province to collect samples of old wood. And you can see some large, relatively old limber pine. And on the ground, limber pine, which has died and is preserved, because this is a dry spot. This is a terrace. This is a sandy soils, well-drained soils. And dry winds come down this valley. And so this wood doesn't rot. It takes a long time to rot. And so we found pieces of wood like this one that date to the year 542. So we have 1,500 years of tree ring data. 542 would be the pith of that tree when it was a seedling. And we've collected wood from 9,600 and some trees over the years. We bring it into our lab. We have a workshop where we plane it and router the wood and sand the wood using belt sanders and palm sanders, and we polish it to a fine finish, bring it up to our dry lab. We scan it on an industrial strength scanner, produce a large high resolution image, And there's my lab assistants, Julie on the left and Nikki on the right, and they are measuring the size of the tree rings. There's an annual tree ring, but it has two parts. So there's the early wood, which is the light colored with the large cells. And then there's the late wood with smaller cells and darker, denser wood, which grows towards the end of the growing season as the soil is dried out and the day length is getting shorter. So we take two measurements per tree ring. We've generated almost 4.8 million measurements of tree growth, and each one of those data points is soil moisture. So we have 4.8 measurements of soil moisture mostly from the prairies. And we have to calibrate, we have to translate the ring width data into some kind of climate or hydrological variable. We know that it is soil moisture that determines tree growth. The problem is there's not much soil moisture data. Well, there's really good soil moisture data for the last 20, 25 years, thanks to the government of Alberta, but they only implemented their soil moisture monitoring program in the mid-2000s. However, there's lots of research to show that soil moisture is highly correlated with other parameters, with other hydrometric or hydrologic parameters, in particular runoff. Because most of the runoff in a watershed comes via the soil and groundwater. Overland flow is extremely uncommon. Most of the water seeps through the soil and under the water table and into the stream. So in fact, runoff is highly correlated with our tree rings because the source of the runoff is soil and groundwater. And there's lots of runoff data. The Water Survey of Canada has been measuring runoff at thousands of gauges since about 1910. So here's our reconstruction of runoff in the North Saskatchewan River Basin over the last 1,000 years. We could spend a lot of time chatting about this, but I'm just going to point out a couple things. These are runoff anomalies. So once again, a wet year is in blue and a dry year is in red. And if you go right off to the far end, that's up to 2021. So it's showing that 2021 was a dry year. There's a large, long red bar. We know that. We know the 1980s were dry. The trees produced narrow rings. The 1920s and 30s show up as drought years. So it is a verification that the tree rings are picking out the droughts. Also note that the tree rings also indicate some fairly wet years in the last couple decades. So the range between the smallest and largest rings, the range between the driest and wettest years is as large or larger than it's ever been. And that's one of the expectations of a warming climate. We expect in the future years that are wetter than in the past, but also drier than in the past. And that seems to be occurring according to the tree rings, but so far we have a relatively small sample size. What I want to point out is the drought, this drought, the dry years of the 1840s, 50s, and 60s. We could go back to the 1300s. There was a wicked drought lasting a century, but that was a different climate period. That was the medieval climate anomaly when the whole world was drier and warmer than at present. So let's stick to the more or less present climate and go back only less than 200 years to the 1840s, 50s, and 60s when there were a lot of dry years. And there were no weather stations, but there were descriptions of the climate, including by John Palliser, whose expedition was sponsored by the government of Britain, and they told the government of Britain that a large area would be forever comparatively useless. They described southern Alberta and southwestern Saskatchewan as useless, but they came through during what was essentially a 2-decade drought. And then the settlers came, and in the very first edition of the Medicine Hat newspaper, there was an editorial that said it was criminal to bring settlers here to try to make a living out of straight farming. But of course, the settlers came because the railroads and the governments encouraged them to come, including my grandfather. So this was the original homestead. This is near Spondon, which doesn't exist anymore. It's near Hanna, Alberta. And disking the prairie sod way back in 1914 at the homestead, which then blew away in the 1930s. So in the 1930s, my grandfather and my grandmother put their possessions and my mother and her siblings in a cart, and they moved up to the farm near Bells Hill Lake in the county of Flagstaff and did pretty well. There's my grandpa stooking wheat. Well, if you want to know more about the tree ring work, it gets written up quite a bit by agricultural journalists. And the tree ring stuff seems to resonate with producers because it's real. It's the climate of the past that actually occurred. It's not produced by models. And so you can see here's John Deere magazine wrote up our stuff. I was asked to write an article for Canadian Cowboy Country, Western Producer, and so on, has descriptions of our work, and you can find that stuff online. And also it gets used. It gets used for preparing drought resilience plans, for example, by the city of Calgary. So their plan that came out recently features tree rings on the cover because they acknowledge our work. So the tree rings and the weather station data and the climate models allow us to study the frequency and magnitude and consequences of drought. And of course, the consequences of drought in the 1930s are very well documented, including remarkable photos like this from southern Alberta and southern Saskatchewan. But even though we still get drought, it's interesting that you no longer see images like this, in particular the dust storms. I remember 1980s, there was some dust clouds that obscured the sun, and but even though there's been some pretty severe drought in the 21st century, including 2021 and 2001, with more suitable, more appropriate agricultural practices, in particular permanent cover and minimum tillage, the risk of wind erosion has largely been managed. And that's, of course, that you're all very familiar with, the really a revelation in farming practices whereby fallow land is relatively uncommon. So this is a remarkable adaptation. And at the same time, there's been an increase in yield, crop yield. This is wheat and canola for Saskatchewan, but very similar trends in central Alberta. And this increase in yield probably is related to climate to some respect, because as I showed, there's an increase in the length of the growing season. There's an increase in growing degree days. So somewhere in this increase in crop yield, embedded in this is a climate signal. On average, the weather is more suitable for crop production, but also, as you know, that the inputs, fertilizer in particular, there's been quite a increase in the use of artificial fertilizers on a lot of the cropland, resulting in an increase in yield bushels per acre. But even so, I mean, you can have all the heat and all the artificial fertilizers you want, but you can't produce a crop in the absence of water. So in these yield time series, you can see years like 2001 and 2021, where there is a major drop in crop yield and some areas crop losses, complete crop losses as a result of drought. But there's an interesting phenomenon going on as described in this headline from the Western Producer. And so far, this is pretty much anecdotal information, but a lot of producers are reporting that they have relatively good, even record crops despite drought and flood. That's adaptation. That's adaptation to climate variability and climate change. But if you read these articles, and the producers they speak to are largely those who are maintaining soil health, are following the principles of soil health, whereby they're trying to enhance the soil carbon, they're trying to elevate soil moisture, they're maintaining a crop cover, they're intercropping, they have I'm trying to avoid the use of the term regenerative agriculture because I know it's controversial, but they're following practices, regenerative practices, so that in their case, they're convinced that they will maintain crop yields despite flood and drought because of the implementing these adaptive practices. And adaptation is the A in our research center. Our center was established in 2000, 25 years ago, to do climate science in support of adaptation. And most of our work is in the ag sector because we were located in Regina for proximity to PFRA. So we worked closely with PFRA until its demise in 2013. And over the course of these years, we have collected a lot of climate data, a whole lot of data. And so we have two 96 terabyte storage devices full of all kinds of climate data, weather data, crop yield data, soil data. And we run all of this data through models like the SWAP model. So we're mapping soil moisture. We use the DSAP model. We're simulating crop yield. So I'll show you a couple, and it's supported in recent years by Southwest Terminal, which is a producer-owned and operated grain terminal, by Alberta Agriculture and Forestry, by a couple banks. RBC and FCC are banks, and they've been supporting it. And we get matching funds from NSERC. So here's a couple. This is our simulation of changes in wheat yield on the prairies from the recent past, which is historical, into those 3 future 30-year periods. And we never use a single model because we can't predict the future. We don't know the future climate. So we take information from a large number of models and look for agreement among them. And the thing to note is as you go from each one of these models from left to right, the boxes are rising, especially the middle and near future, which is higher crop yield. But then it kind of levels out. Other levels out or even drops in the far features. So the conclusion is that some global warming is great, too much is not. You get into a situation of heat stress. Other thing to note is the whiskers. The whiskers are the extreme values for the 30-year periods. The whiskers, the range between the lowest crop yield and highest is going larger as we go forward. So we can expect some unbelievable crops, bumper crops, but also still crop losses. So this is our simulation over time. And this is over space. We're mapping it because, after all of the data we have is geospatial. It's all on grids. And so Zara, working with Dr. Zara Mohammed and myself. So this is the ag zone across the prairies. This is those 3 greenhouse gas emission scenarios. And this is the change in canola yield. And I think the point out is by the middle feature, we can expect a drop in canola yield in the driest parts of the prairies, but an increase in canola yield in the more northern and western part of the prairies, where historically there's been a heat limitation, a growing degree limitation. And so it's largely good news for central and northern Alberta in terms of canola, because according to these scenarios, especially the first 2, it's getting greener or higher yields. Now, this assumes rain-fed agriculture, and it assumes current farming practices. So the next phase of our research is to take this baseline, which assumes rain-fed agriculture, and the models are trained on historical yields and past practices, and to update it by introducing various soil, water, and crop management practices, like changing seeding dates and so on, and see how we can maximize the benefits of a warming climate by incorporating all of these adaptations that producers have begun to implement. But we're going to scale down right down to the township scale. So we're going to look at 2,000 townships because we have very detailed data. And also we're going to say, okay, here are the potential benefits, but what's the downside? The downside is when the drought of the 1840s and 50s reoccurs. What's going to happen when we get a 20-year drought? How well prepared are we? So this is the next phase of our work, and we're seeking funding for this right now. That's it. Hope I left a few minutes for questions.
Perfect. Thank you, David, for this amazing presentation. Now I will open the floor for Q&A section. If you have any questions, you can feel free to type it in the Q&A. And if there's someone who doesn't know how, like it's not good at typing, they can always raise their hand. Oh, I see a lot of people already leaving. Interesting.
Well, it took 45 minutes. I thought it was going to be 30. Sorry.
Oh no, it's like perfect. Normally, I think so. Your presentation was spot on. So I think so. They didn't have any questions. I'm assuming. Is there anything else you want to conclude your presentation unless people are typing?
Yeah, well, I guess the take-home message is don't believe what you read online, because all of that is about global warming. And it's an unfortunate term, global warming, because there is some climate change, but the regional climate change can be very different from the impression you get by studying the whole world. And I've tried to show using Lacombe that what's happening in our part of the world, it's not getting warmer, it's just getting less cold. But there are consequences of a shorter, warmer winter and a longer frost-free season. For the most part, they are good for agriculture on the prairies, but not everywhere. And not in years in which we're lacking moisture, because that's the ultimate constraint on agriculture in our part of the world, is the periodic drought.
Perfect. I guess I don't see any more questions. So
This is back to the farm near Bells Hill Lake. So
yeah.
this is what the farm looked like and what the barn looked like back in the day with the brand up there. Okay.
Okay, I guess then we can conclude the webinar. There's no question. I guess you did an amazing presentation. So.
They can always email me. That'd be fine.
Yeah, that's what normally I tell everyone in the end.
Sure. Yeah.
Thank you, David,
Thank you, Bear.
for giving us your time today and sharing this valuable insight. We truly appreciate your contribution. And thank you, everyone who joined us today. Thank you for giving us your time to being here. That brings an end to our webinar. We hope everybody found it informative and worthwhile. If you have any feedback for future topics or webinars, please don't hesitate to reach out to us. And if you have any more questions for David, which you were not able to answer or ask, you can always send me an email. I can forward it to David. Thank you again all for coming, and I look forward to seeing everyone at our next event. Yeah, thank you so much.